Well, hello everyone. This is Philip Moan. I am the chair of the Houston chapter of the IEEE Power and Energy Society, and I want to thank everyone for coming. We got a great presentation today, and I want to thank all of our co-sponsors for the event: the Southeastern Michigan um, chapter, the Milwaukee chapter, the Connecticut chapter, the Baltimore chapter, the New Hampshire chapter, the Cedar Rapids chapter, the Green Mountain chapter, the Black Hills subsection, the Providence chapter, the Northern Virginia and Washington chapter, the Boston section, the Denver chapter, the South Plains section, and the Atlanta chapter. So we've had a ton of support publicizing this event. I'm really excited to introduce our presenter today. He's a professional engineer with 9 years of substation experience in protection and control and physical design. He's executed substation projects for over a dozen utilities from the East Coast to the central US. So allow me to introduce Jeffrey Zelinski. Go ahead, Jeff.
Hey, thanks, Phil. Appreciate you all for hopping on, and I hope you guys enjoyed this presentation I have for you. My name is Jeff Zelinski, as Phil said. Been in the field for 9 years and been working with Orbital for a little over a year now as a senior electrical engineer. So thank you again for all hopping on. Um, Today's presentation is going to be on substations connectors. The overall goal and purpose of today, sorry for that slide delay, is to help you guys identify the different types of connectors and substations and the ideal uses for each type of connector, and be familiar with the physical, environmental, and material science impacts of choosing and installing the proper connectors. So I always like to start off with the basics of what are substation connectors. There's varying different answers you can give, and some of them I like to use are: it's the parts that connect different elements of a substation together while providing a reliable low impedance electron path for the transfer of electricity. Some would say they must be picked out to account for the forces due to faults per client standards and preferences. Ultimately, I like to say they're responsible for connecting the above grade electrical system as well as the entire grounding grid system. Um, in short, they're like the knots that tie everything together. Now, when you go into thinking about what type of connectors and all the different situations you would come across in a substation, I like to ask myself the three following questions: the what, the how, and the why. Now, what is the main function of this connector? Are we terminating onto a switch pad, a transformer pad, a breaker pad? Are we tapping off a main bus run to CCVTs or to station service? Are we expanding a bus? Maybe we have a breaker and a half scheme substation and we're putting in a whole new bay and we need to splice some new bus to an existing bus section. Then we can get into the how. Well, how are we going to perform this? Are we going to use a compression style or a welded style, or are we going to use bolted? And then the $1,000,000 question is always the why are we choosing this type? And generally the answer is based on its application. Is it, oh, we're going to use compression with underground T's because let's say DMC power connectors compression style is our client's preference? Are we going to use CAD weld and make welded connections for the ground grid? Are we going to use bolted for non-full tension style connections tapping off of a bus span? All these should be able to answer based off of your function and your type, and ultimately what's your application use for it. Another way I kind of like to look at your design choice is designing with balance, and essentially starting at the 1 o'clock with safety and working my way around here. Safety, are we choosing a safe design? Not just for the power grid for our customers, but even for the field crew that is going to be installing this equipment. Are we thinking about the conductivity? Are we have the right size conductors and connectors? Or are we going to be the limiting factor? Reliability. If we choose the wrong type of connector, that can affect the longevity of this spot, and then thus unforeseen shortcomings can trickle down to unnecessary power outages. Preference: do our clients have a preferred vendor list? Do we prefer specific types of connectors? So do they favor bolted over compression? What is the location of this station? Is it near a large source of water? Is it a commonly humid area? Are we in a high or low altitude? Is heavy wind or ice loading a common factor? All things that could also affect your design choice. And then the economy side of it. Is this design economical? Is it cost efficient? Is it something that your client is not going to look at you wondering why you made this choice? And we'll get more into the pros and cons of those types of decisions as we get into the different connectors. But before we go into connector types, one thing I like to kind of go over is just discussion of conductivity. You'll see a lot that of times you'll come across copper and aluminum as the two most common conductors in pipe that you'll see. And copper and aluminum offer different levels of conductivity and require an intermediate connection if you're trying to prevent corrosion. Now, what you'll see here in the top left corner of this chart is that a 2-inch aluminum pipe compared to a 2-inch copper pipe are going to have varying levels of ampacity. So always know that it's not a one-to-one when you're thinking of the two styles. When you have two dissimilar metals and say they are immersed in a rain or fog, it can take up a corrosion potential. And when two metals have a different potential, currents will circulate between the anode and the cathode, causing what is known as galvanic corrosion. So in situations where this may happen, you'd see it, say, on a overhead dead end structure, you have your steel line or aluminum or steel coming over the top and coming down the structure, and then your ground grid is usually consisting of copper. So this would be a situation where you'd want to try to have something called a bimetallic transition plate. And that is where you're joining the aluminum copper at the atomic scale. So that if you put an X-ray up to it, there's no air gaps or holes for water to seep in. And then this allows for no electrolyte to facilitate the corrosion process. But let's say you cannot find or use one of these style bimetallic transition plates, then another option you could use is something called a tin connector. Tin connectors are a good intermediate for when connecting to copper or aluminum, or you could even utilize a tin bar, say a 4-inch by 10-inch by 1/4-inch thick, where you land the 4-hole pad of the copper on one end and 4-hole pad of the aluminum on the other, or 2-hole, depending on the size of your connectors. When, say, there's a situation comes across where you are not able to have a tin member or a bimetallic transition plate, always what I suggest is to make sure your copper member is placed on top of your your aluminum member is placed on top of your copper member. So in the sense of if it rains, those copper salts will start to wash down into the joint if it's placed on top, and that'll start the process of galvanic corrosion. Another area I like to talk about with conductivity is microscopic asperities. Here's an example of a bolted connector where you'd have your cable coming in and a 4-hole pad. And this could land on a switch pad, a breaker pad, transformer pad. And what you ideally want to do is make sure that you have a good contact surface. That is the key for proper electrical connections. And you want the most uniform roughness to provide those most contact spots. So you'd want something, I know this is just a simple little drawing here, but you'd want the most uniform roughness here, so then you are completely utilizing the full contact of the two 4-hole pads against each other. Something else that will be inside of here, and we'll talk about it in a little bit, is the use of an oxide inhibitor. Now, when you press down on these, because these forces are going to be dependent on the force of the two 4-hole pads pushing against each other, how hard their surfaces are, and the assembly process, making sure you're correctly tightening the bolts to the exact torque value that's required. And as I mentioned, adding that oxide inhibitor to make sure then you are giving the most sound electrical connection. But over time, what you'll notice through small amplitudes of movements by changes in temperature and vibrations at 60 hertz. Vibrations will start to occur. And then what you'll notice is those peaks are going to start to get sheared. And that's where your uniform roughness and your asperities are not going to line up as they were prior. So then you'll start to see these gaps, and that then thus affects the resistivity of your connectors and the conductivity that is allowed. So getting into some of the different types of connectors we're going to discuss today. There are the cable to flat. So you got your ACSR, your AAC into a flat 4-hole pad, and there's the welded style, the compression style, which they also have a swage, and I'll talk about the differences of those two in a little bit, and the bolted style. And then for cable to cable, this is more compression or bolted for when you have T's or you're trying to splice two pieces together. For your bus to flat, that's similar to your cable to flat, except you have your aluminum or your copper bus, and you have the methods of welding, compression, but swage only, and bolted. And then you have your bus to bus connectors, which you can use the welded method, the compression, or the bolted method. And finally, we'll get into the bus support fittings of your rigid, which is your fixed, and then your slip and expansion. And then after that, we'll go a little bit into some of the failures or things you can think about of how to prevent shortening the life expectancy of some of these situations. So starting off with welded type connectors, I have two pictures here. The first one at the bottom is showing you cable to flat, two conductors coming in where they weld the actual conductors to this connector member. And then you'd land your 4-hole pad on your switch pads, or if it's jumping off of a bus run or a transformer and breaker. So welding provides a strong maintenance-free connection, and it provides atomic level fusion. It melts the two shapes together so they become one homogeneous joint. And if welded correctly, you should see no spaces between the two surfaces when x-rayed, and you then be considered a maintenance-free connection. You won't have to come back and reevaluate every so often. But the one of the downsides of a welded connection would be that it has to be performed in good weather conditions. It can't be really done in inclement weather because if water gets into it, it'll create some voids, and then that won't be as strong of a hold. Some other facts to consider when using welding. For this picture here at the top, we're showing this is low bus support to high bus support, just showing on the A-frame members how they welded the bus to the connector as well as the side members of the A-frame. And when you go to make a weld to say splice two pieces of bus together, you're essentially lowering the elasticity of the bus. So you want to make sure you do your bus calculations. On top of that, you're also reducing the bus strength by about 50%. So a rule of thumb, example I like to give is you always want to make sure your splice point is within 25% of the span near a bus support. So if you have two bus supports and they're about 20 feet apart from each other, you're going to want that splice to be within 5 feet of one of the two bus supports. Another thing to consider is when you're doing your design and going back to client preference and the economical side of things, you always want to consider if I am doing part of a station where we're going to have over 200 connectors we're installing all over the place, and let's say only one or two of them we for some reason chose welded. Well, welding is going to require someone with specialty skills and specialty equipment, and in the big picture, is that going to be cost effective versus if you say half of what you were going to do is being welded? Because otherwise, if you're only going to have a few positions, you might want to look into potentially a compression or a bolted connection that might be faster to install and less expensive. But moving forward into another style, which is compression connectors. So compression connectors and swage connectors are pretty similar. I'll describe the differences, but both of them are very versatile. You can use them for this picture as a terminal connector where you're tapping off of the switch pad or onto the circuit breaker for a whole pad, or you could have it in this picture at the top here is an example. It's actually sideways. It's really coming from overhead line coming down, and we did a compression T connector. And then you can also use these compression style for splicing. These compression connectors, as you can see, this one here and this guy that's zoomed in is actually this middle phase on the breaker down here, are really good for full tension design. So if you had a long bus span and you were jumpering down into a bay, like a breaker and a half scheme, that let's say the outer phase, outer bus that has to go the longest span, there might be a lot of extra length and weight, and we want to make sure we're providing the correct cable or conductor that will hold it and not risk damaging the line or having it fall out from the connector. So using a compression style over a bolted in a full tension design is highly recommended and preferred. And if we're looking at this picture here, you can see tiny little lines. And this is showing you they actually crimped this 1, 2, 3, 4, 5 times. You work your way from the 4-hole pad to the end of the barrel when you're crimping. And if you guys can see me on the camera, the difference between a using a compression versus a suede, if you were to take your hands and make 2 circles and push inward, where your left hand is pushing to the right and your right hand's pushing to the left, you essentially only have 2 forces pushing inward. And that is what a compression connector is doing. It's basically smushing it top, bottom, left, or right, and smushing the barrel to the connector. And going back to the 4-hole pad with the oxide inhibitor, you'll also have another style oxide inhibitor inside this barrel to cover any air gaps. And the reason you want to crimp from the 4-hole pad outward is that as the excess inhibitor, as you get closer to the end of the barrel, all that excess will start to drip out. But you'll have a solid connection from the barrel with in between it being your inhibitor, filling up any gaps, and then your conductor, and have a sound connection. Now for a swage style, you imagine having 360 teeth all in a circle pushing inward at the same time. And that is where then you'll see these lines still, but there'll be 360 little teeth mark going all the way around the barrel. It's giving more of a 360 inward push rather than 2 forces. Some other facts just to know is if you do this correctly and you do enough crimps, because if you don't do enough crimps, then you're risking the chance if you need it for a full tension design situation, you will need to crimp it all the way from the barrel to the end. And then essentially like welding, if done correctly, it will be a maintenance-free design. You should not have to come back to check on it every so many months to make sure that the compression connector is still working and has a sound connection. Another thing you need to know is that it will still, like welding, require special tools, dies, and training. And it is a better oxide inhibitor holder than a bolted connection. But going back to my example, if you have 200 connectors in a yard, using that tool to crimp each connector multiple times is going to be physically fatiguing, but still has more pros than some other situations. Now, if we go to another style, which is the T connectors, this example here would be one where you take a 4-hole pad and you would just say weld it onto this bus. This picture on the top right has an example of a bolted style T connector. And then this is actually an example for an underground here in the bottom right-hand corner, where we essentially, this would be for the ground grid. You'd have your main run here, and let's say you have a pigtail coming up above grade to then land on the structure leg. Similar with the compression style, this black line here is actually a piece that you can take off. You lay your main cable run in here. You hammer that top piece back on. You push your tap pigtail inside on this part, your tap, and then this shows you the lines of where you would crimp. So you'd work closest to the middle and crimp your way out on the barrel on both sides and then on your tap. But just to show you 3 different examples of how you could do a welded versus a bolted and how compressions are used. And they do have compression style for bus as well, where you can do compression and then you have your 4-hole pad. But T connectors are really valuable for helping you to tap off of midpoints of a cable or a bus run. When you have a downcomer, like you see in the background here from the incoming line, you can tap off onto your lightning arrestor. So there's There's many values for a T connector, and it's commonly used for instrument transformers, wave traps, and line arresters. Now, bolted connections. For both these photos here that you can see, here's a bus to flat bolted style connector, and then here's a cable to flat style connector. And so bolted mechanical connectors are easy to install. They have different torque values for them, generally are listed on the connector itself to tell you exactly what values to tighten the bolts to. You'll use lock washers and bevel washers to help prevent loosening over time the bolts, but they will require maintenance every 6 months to a year or so. So that's something to consider, that you'll have to constantly go back out there and make sure that everything is to the right amount of torque. And these would not be something you'd want to use in a full tension design. But to get a little more into the torque side of things, I like to put this graph in here as a 4-zone process. I added a 5th zone myself, but essentially the process of tightening the nuts and bolts just involves turning the bolt and related torque, getting it to that desired value, so the clamping force will hold the nut and the bolt together and give you that sound electrical connection between your 4-hole or 2-hole pads. In the first section, the rundown zone, this is essentially the part where you have your bolts, your nuts, your washers, and you place them there, and it's just sitting against it. There's no pressure pushing the 2 4-hole pads together. You're just in the beginning portion. And then when you transition to the alignment zone, this is where you're starting to tighten it, and there's starting to be a little bit of joint mating surfaces, alignment. The bolts are starting to line up. Everything's starting to almost start making some contact. And then when you start feeling that pressure towards the 4-hole pad, 2 4-hole pads together, that is the elastic tightening zone. And this slope is the torque with respect to the angle is constant. And this is where you'll locate the elastic origin for each bolted joint. Once you get to its inflection point at the end of the elastic zone, the yield point will be then used to tell you exactly how much more torque you need to provide to have that sound electrical connection. And depending on the number of bolts, the type of connectors you have, the thickness of the 4-hole pads, they vary in this plastic tightening zone where your optimal torque will be for the bolted connection. And then what I like to add is the 5th zone is if you go too far and you over torque it, you go to the failure zone where you're either breaking the bolt, you're breaking the nut, you might crack the 4-hole pad, and ultimately have to get a new one. I like to add this slide into just for some food for thought. You might come across different situations between copper, aluminum, and steel, or any combination between them. But the one thing I want to point out is, if you notice, for your bolt, your nuts, your flat lock, and Belleville washers, every combination has a similarity in that stainless steel is a good intermediate choice between similar copper to copper, copper to aluminum, steel to aluminum, aluminum to or steel to copper then. So always consider the option of choosing stainless steel instead of, because if you order, say, an aluminum connector and you don't specify stainless steel, they're going to send you aluminum nuts, bolts, and all that. It's just something to think about for future. So getting into bus supports, first with the rigid and slip, I like to kind of combine them on one slide because they both will look very similar in design. However, a rigid one will weld or compress the bus to this support member. So if it's a welded, you'll have just an easy weld right around the perimeter here, or they might have this member project out a little farther so they can compress it on both sides. It anchors the forces to the insulator and the structure, and it allows the least amount of thermal expansion, and it will inhibit the most movement. Now, for a slip fit style, it inhibits movement, but it transfers the gravitational force to the connection point, but then it'll also provide that axial motion for the thermal expansion to move. Not all have this static guard right here. which is labeled as spring up here. The static guard's purpose primarily is to limit the vibration of the bus, but another tool you can utilize to limit the vibration of the bus would be to actually place a conductor inside. Say if you had a 4-inch aluminum pipe here, you could always add like a 795 conductor inside, and that'll also help with limiting the vibration. Getting into the third type of bus support fitting is the expansion fit. So this is transferring gravitational forces and lateral forces, but it's important in diverse temperature regions along bus spans. Personally, I always like to think of the combination of rigid slip expansion and repeat that. And you could always use an expansion could always be considered at the end point of a bus run too. If you just have it end, it's just capped, that can actually count as one of your expansion points. But to dive a little bit farther into thermal expansion, to decide when would you actually use each type of bus support fitting, because the goal is to allow for the movement of the bus due to thermal expansion. Thermal expansion is the tendency of matter to change its volume in response to change in temperature, and thermal expansion always needs to be considered when choosing bus connectors. It's usually based on a 30°C rise over a 40°C ambient, and it's ultimately the temperature is based on a mass versus surface area, a heat generation versus a heat dissipation situation. And then when choosing situations, say like for dead end connectors, you always need to consider thermal expansion, because transmission line conductors are typically run at a higher temperature and rated differently than the same conductor would be in the substation. So that is always something you would need to consider as well. But as I was saying, with the idea of what types to choose in what order, you can count an A-frame typically as another rigid position, and you always want at least one expansion point, which you could say the end of a bus run could be an expansion point. But at a max, you can fill in 3 slips in a row. The danger with adding multiple slip fits in a row is you need to make sure your bus calcs are okay, because it risks the chance of the bus binding up at one of those slip points when it's not supposed to be. Getting into a little bit of grounding, both above and below grade grounding. There are different types of connectors you can use there as well. The first one here, the crimp, is this bottom left one here, where you essentially are just smushing these two members with the two conductors that are going through it together. And then a similar fashion is these two bolted styles, where you essentially you're bolting into the structure. And then if you say this was your ground pigtail coming up, and then you had another one because you wanted to ground the side of the circuit breaker cabinet where you had a second run, whereas this, then you still wanted this one to continue upward to have another connection to the structure holding the equipment. That's another possibility. And again, this would be mounted or bolted to your structure. And then when you get to the below grade style, I showed you earlier the T connector, where you could compress both sides, and then you have your pigtail tap to go up. Instead of doing a compression where you crimp on both sides, you could do this CAD weld method, which is most commonly used. And you have to make sure it's not inclement weather, but you're essentially welding these points together at an atomic scale. So you'd buy your mold that you'd have, whether it's a T or a cross mold, and then you essentially put in kind of like almost like gunpowder in there, and you do an exothermic weld. It offers the best connections for underground with extra moisture retention. But again, like I said, you can't do, it's not advised to do in inclement weather, and will risk having some voids if water would to seep in. Another topic I want to just cover real quick is bifurcators and trifurcators. So this would be the example of if you had this bus run, and then you decided, two 1590 ACSRs is more efficient than doing one larger conductor, but you bought 2 individual cable to flat terminal pads. You could essentially lay this 4-hole pad on the cable to flat connection for the bus to flat connection, and then put your 2 terminal single barrel connectors right here, or, and as you see in this photo, vendors also offer like dual cable to flat, so then you would avoid even the use of this. But I like to just put it out there. They do have a 4-hole pad to 2 or on a 4-hole pad to 3 type options. So just always remember there are other things out there, designs that might be better to suit your specific situation. Another thing I'd like to note is you never want to lie more than 2 4-hole pads or 2-hole pads on top of each other. Going back to thermal expansion and the vibrations due to the 60 hertz, that will start to shear and chip away at both the top and the bottom connection to the middle 4-hole pad, and just pretty steadily increase the resistivity that we don't want there, and those air gaps that won't help. Getting into dead end style assemblies here. I call this one the dead end pistol grip strain clamp, where you'd have your incoming overhead conductor coming in and goes down through here. You have your bolted connection holding it into place. And in some stations, you'll see where that cable might continue onward to the switch pad of the first switch in the yard there. At this point, you'd have your clevis, your Ys, your insulators, and then that would attach to your dead end structure. Another thing you could do here is if, say, the rating of the cable in substation's not rated high enough for the overhead line, you could always cut that cable past this point and then get a compression, a bolted, or even a welded T connector to then drop down into your substation yard. Another style dead end, I have a couple pictures to show after this slide. This is the compression style dead end assembly, where again, this would connect to your insulators, your clevis, your Ys, and to the dead end structure. This would be your overhead transmission line coming out to here. And then this is the example of a single tongue horizontal eye. You could actually have 2 tongues where one goes up and over top. If, say, this is a transmission line that wanted to have a down drop into the substation, but then go up over the dead end structure and continue onward if the circuit was to continue. With this, then you have your compression connector. It's showing you the dashed lines of where you'd want to crimp, crimp, crimp on your way out. And to show you how they install this, I'll show you over the next 2 slides here. So in the first picture here here's your single tongue compression connector. And what we're doing here is we're taking this to the end of the barrel, and then we're going to mark that just so we know how deep is this going to go into this barrel. Then we actually use some tools to cut and just keep only the core, and we put this mold in there with it. And before we then put this into the barrel, we want to brush it to maximize the asperities and have the most uniform roughness, and make sure we minimize the amount of air gaps or water that will seep in. And in the next slide, we'll be able to show you, this is having the member now attached to the inner core piece, which then they'll start to push into the barrel. And this picture right here is a good example to show you the compression connector. You only have 2 members, the top half and the bottom half, pushing inward to crimp this inside the barrel. Whereas if this was a swage connection, you would see many little teeth, and they're all pushing inward rather than a downward and an upward force. And then this picture I like to use is as you start to crimp it, you'll start to notice the oxide inhibitor starting to seep out. There will be a little hole at the end of the barrel here where you actually take your oxide inhibitor to fill it once you put your cable inside. One topic I always like to bring up as well is corona. As you get to the higher voltages, corona becomes a factor and plays a larger role in the design of connectors. Usually when you get to over 230 kV and above, and corona will cause audible noise, electromagnetic interference, and insulation damage. So what you'll notice in terms of connectors themselves, you'll start to see that they will start to be a little more smooth. They won't have as sharp edges. This will reduce the pressure of dielectric strength of air and lower/help mitigate corona. You can notice even the barrels have been shortened a little bit, and even in a regular style situation of a a compression terminal connector, you can order a short barrel if it's a situation where you don't want the barrel to be too long because you're worried about electrical clearances or any issues like that. But you'll also see here that they still used a compression for this specific connector. So getting into some of the failures of connectors, what can go wrong and why? We kind of went a little bit when we were talking about microscopic disparities with fretting wear. I know this picture, this isn't a typical connector or anything you'd see in a substation yard, but it was a good example to show the wear and tear actually on this material. And that was generated by the small amplitude of movements and change of temperature and in the vibrations at 60 hertz. And during that, that's when friction lets off the small debris that oxidize quickly. In this picture in the bottom left here, it shows you when you use clamping methods that at points of stress, material may clamp, creep, and elongate, which will cause failure. And as the conductor starts to heat, then you're getting a similarity to the annealing process, where essentially you're heating up a conductor past its recrystallization point. So when you have a line and a long span, you always worry about sags and the sag charts. And if you run at a higher temperature, the sag's going to be increased. Now, if you heat it up past a certain point, then that sag is not going to go back to its normal state. And that's what you can kind of see is starting to happen in this situation. And then ultimately, it makes the metal more ductile. The third and fourth reasons of failures: oxidization. Oxygen plus heat creates a resistance coating on a metallic surface. It's only for copper is it dependent on temperature. For aluminum, it's dependent on temperature and humidity. And in terms of corrosion, that's the deterioration of metal in the presence of water, where metal loses ions in water solution, and aluminum corrodes much faster than copper would in those situations. And then lastly, I always like to add the human error. If you think of a bolted connection, if they don't screw all for a 4-hole pad, all 4 bolts to the maximum correct tension, if they over torque it, they under torque it, if they don't, in a compression connection, don't do enough crimps, if they crimp it the wrong way, from the end of the barrel to the 4-hole pad, when they're really supposed to do from the 4-hole pad to the out part of the barrel. Many things can happen in terms of human error, and it just goes to show, even if you have the best design and you've thought through everything, there is still other things that can happen. But now thinking about the idea of prevention, this picture here on the right, this is an oxide inhibitor, and you see the words non-grit. So non-grit is for the 4-hole pad to 4-hole pad connections. Then they have a version that's called grit, which it has zinc in it. And essentially, when you say have the compression connection with the long barrel, and you have your conductor in there, you fill it with this oxide inhibitor, and the zinc will fill up all the air gaps that are left to then give you the sound electrical connection that you were looking for. You want the non-grit for the 4-hole pads because you want it more as like a grit or a grease that adds more so than to cut into the material itself with the zinc. The correct inhibitor is always necessary for each connection, and that is something that can also help in the prevention. But to compare, say, a compression connector versus a bolted, if we look at my next slide, the reason you'd say a compression connection holds the oxide inhibitor better, as you can see, there is a gap here where you can see exposed cable. There's no way to keep it all in like you can for a compression connector that has a barrel with no way to see into it. And this would be the example or area of where you put the non-gridded oxide inhibitor. And again, another way to prevent is you make sure you brush your connectors, your copper or a conductor, and try to really maximize those disparities. So I know I probably went through a lot of material there with you guys, but I hope by the end of this now, maybe there's a lot of this you might have already known, but maybe there's a few new things. And if you learned one new thing, I call that a victory. But hopefully you're able to identify the different types of cable, bus, and grounding connector types and when to use them. And if you ever come across situations with copper and aluminum, what to do or how to best handle those situations. and just have maybe a better understanding of the physical and material and environmental impacts that can come into play. But the last thing I would like to say is just always remember there are different types of situations out there that might be completely unique to your project, your station that you're working on, and don't be afraid to reach out to the vendor and see if there is a unique custom style connector that they can make for your situation. There's always going to be something out there that might be just ideal for your specific situation. But with that, I would like to say to all of you, congratulations. You guys are all now experts at the nuts and bolts of substation connectors. And I'll leave it open to see if anybody has any questions. And I just want to thank everybody for your time. Yes, I see Peter.
Yes, can you hear me?
Yes.
Yeah, thank you for the presentation. I had a question. It might be a bit off topic, but rebar, like used in padding and whatnot, when does that need to be grounded? What would that be, a CAD weld or?
So for rebar, I will say it's not particularly my area of expertise, but typically when you're going to ground a structure, you would come, say, connect from the ground grid, come up above grade, and usually right at the bottom of the structure, whether you have like a little flange off the edge of the steel or they'll have a dedicated pad, is usually how you would connect to that. And then I know some utilities I worked for would maybe pigtail off of that and say wrap around one of the rebars that come above the foundation grade. I hope that answers your question.
So would they, rebars are steel, they would connect to that with a connector using CAD wells or to make a connection to it, or?
You could use CAD weld. One thing you just want to, it would be either that or I would imagine like a bolted connector, just wrapping around the rebar, and maybe you'd have your other connector if you had like two side by side where you can put one as your rebar and then the other as your ground pigtail coming down.
Okay, thank you.
I see Jacob.
Hi, yeah, can you hear me okay?
Yes.
Awesome. Yeah, great presentation. Thank you. My question, and this might be a little too broad or might, but just how does fault forces, how does that kind of go into the design of picking connectors?
So when between doing both your bus calculations and then just looking at what is your limiting factor, say for just different connectors, making sure you are essentially not the limiting factors, the way I always try to look at it, in terms of just you don't want that to be your weakest link. And as long as you have other pieces of your equipment or the rest of your substation above grade electrical assemblies are all rated adequate and such that it's not the limiting factor, and say maybe like your incoming transmission line might be your limiting factor, that's how I consider accounting for those fault forces and situations.
Awesome. Thank you.
Thank you. I see a Fritz.
Can you hear me?
Yes.
Sorry. All right, cool. Awesome. Thanks for the presentation as well. I have a couple of quick questions. One's for the compression. I mean, if we have compression fittings and for some reason, I know on the compression fitting, it calls out the die. Is there multiple dies when you utilize those, or if there's one that's similar in size? I mean, obviously there's failure for getting the correct compression on there. But sometimes I've seen that there's multiple die sets for those compression fittings, right?
Yeah, so essentially you'd have like a piece of machinery and it has your handles, and inside where you'd have the two forces that are actually doing the compression, those are the dies that will be sized accordingly to the size cable or the bus that you're trying to compress to.
Okay, so that should be called out based upon the conductor and the compression fitting that you're using, right?
Correct.
So, okay. Second quick question. It would be for the bolted connections. In reference to that, would the manufacturer specify the grade of the bolt with that connector as well?
So typically, I was trying to use a slight example earlier. Like if you bought, say, a terminal, a cable to flat aluminum compression connector for a 795 ACSR, they will more than likely provide you aluminum bolts, nuts, and washers, all that material, if you don't specify, say, stainless steel.
Okay, but they would also specify like the grade, if it was grade 8, grade 12, or would you have to specify that based upon the requirements for the substation work that you're doing for the owner?
That is a good question. I would want to believe they'd have it specified for each connector that they are designing for. However, I would definitely double check on that. That is a good question.
Okay, thank you so much.
No, thank you.
I appreciate it.
And I see one more, Daniel.
Presentation. It was great. Quick question on compression terminal, like on the breaker that you have shown. We have a lot of freeze thaw in our area, and we've had our compression terminals split at the end or crack or break. We've gotten different recommendations to either drill like a hole in the bottom for water to seep out or to not do that. Sometimes they say the grit is enough to hold all the water and moisture out, but any recommendations, like would you recommend putting a hole in the bottom so water can seep out, or just leave it as is and just deal with it?
That is a good question. I know, say, for the dead end compression assemblies or the incoming lines, they'll actually plug that hole in after they fill it up and then crimp all the way up to the end of the barrel. Typically, my thought process, both from a conductor standpoint and a bus standpoint, when you have a long bus span, I know substation yards aren't supposed to be more than a 1% slope, but there is usually a little bit of a slope. So you'd want to have, say, for a bus, like an aluminum pipe, seep hole at the end where it's going down towards the one end, so it'll drip out. Typically, if you'd add a little seep hole for a connector, say for that breaker example, those connectors are up on an angle, so it might be advantageous on top of adding the oxide inhibitor. Whereas other situations, if your connector is kind of flat, you might be able to get away with just the oxide inhibitor and not have to worry about it as much because you're not guaranteeing it all to drip then down to the end of the barrel. But then it sounds like the damage is incoming where the water's staying in there, and then when it freezes, it expands and cracks. If I'm hearing that correctly.
Yep, it is. But I think like what you said is for like the breaker situation, drill a hole in the bottom. Any idea what size hole?
Typically, I wouldn't be able to give you an exact dimension, but they're tiny little holes. If I go back to the slide with the oxide inhibitor, you really don't need a large hole to even insert those into. So it'd be a similar mindset with just making sure that you have some way of or method of the water then to seep out.
Okay, awesome. Thank you for the help.
Thank you. And I believe
on the
oh, sorry.
Yeah, no problem. On the weep holes, it's a good idea to drill it after you've done your compression. Because if you have a weep hole pre-drilled, when you start doing your compression, it'll just squeeze all the inhibitor out of the weep hole.
Absolutely. Thank you for that. And I believe I see a Thaddeus has hand raised.
Very interesting. How are any of these considerations affected by high voltage DC as opposed to traditional high voltage or extra high voltage AC?
That is a good question. I would have to try to do a little. My experience is more on the high voltage AC side, so I don't want to kind of lead you astray in there. But
Yeah, certainly the
giving you an
corona
answer.
issue is different, obviously, with high
Correct.
voltage DC. Then, but all the other ones it would seem would be probably not so different, except maybe some of the corrosion issues.
Yes, and that is one I always like to say is just always remember one thing is keep your aluminum above your copper.
Thank you.
Thank you. I see a Jim with your hand raised.
Yes, thank you. So, got a quick question, on the bus support, fitting. So some of the fittings, from the supplier, they said it could be either rigid or slip. So it's a rigid slash slip. I think they can rotate the top cap to create either a rigid or fixed connection or slip connection. Can you elaborate on how that works?
Yeah, so the two types of the rigid and the slip are just very similar in terms of how they appear. Whoops, I'm going the wrong way. Apologies here. And essentially, it is more so that you would either be able to weld, say, the rigid side, or you'd actually weld the bus portions to the outer ring. Here we go. To this portion here. Or also I've seen situations where this member can project outward a little, and then that would be a compression portion as well. But for this specific photo, you are correct. This could be a one of those where you tighten the bolts down to kind of pin the aluminum or the bus into place. And then Nick Matone, do you have another question or
Oh, no,
apologies.
sorry.
Oh, no, it's okay. I just wanted to double check. If there are no other questions, I'm going to transition to our last segment here really quick, where, about that, Ed Miller, Director of Substation Services, is going to give a quick spiel here for Orbital Engineering.
Yeah, great. Thanks, Jeff. Appreciate the detailed presentation. Just a reminder for everyone, PhD credit certification will be provided, and the presentation will be uploaded to YouTube, and a link will be sent out for that. Just wanted to provide a quick high-level view of Orbital Engineering for those of you who may not have had the pleasure of working with us previously. Orbital Engineering is a full-service engineering and inspection firm specializing in retrofit engineering, large grassroots projects, and complex inspection programs. Orbital's been in business for 53 years and has 500 plus employees, and service our clients through 9 different locations throughout the country. If you just jump to the next slide, Jeff.
Yes.
And then just a quick highlight on utility services. Orbital Engineering's energy transmission and distribution clients rely on our services to provide efficient and cost-effective solutions for a wide range of services. We're currently operating in the transmission and distribution line design, underground distribution design. The joint use space, this includes program administration for telecommunication companies, and make-ready design and construction. We're a full-service electrical substation design firm for inside the fence engineering. This includes brownfield and greenfield design for 400 to 500 kV. We provide full protection and control design services, physical outdoor electrical design, and civil structural design. With inspections, we lead a QA/QC process provide construction services for PMs and CSCs and outage planning, as well as utilize advanced technology for 3D scanning and modeling technologies. With that, that's just a brief overview of our utility services, and I'd like to turn it over to Phil here to close us out. So thank you all.
Absolutely. Well, thanks. Thanks so much for the presentation, Jeffrey, and thanks for that, Ed. I just want to thank everyone for coming again. I want to thank all of our sponsors for publicizing the event, and hope everyone has a good afternoon, and look forward to seeing everyone at our next webinar. And with that, I guess I will go ahead and close it out.
Thanks, Phil.
Thank you.
Thank you.
Thank you.
Thank you. Thanks.